In this exercise is asked to provide for a stochastic process several other questions to answer to other questions. First of all, the new exercise has got as a new entry the fact that the parameter for Bernoulli is lambda over n. Well, both of them represents a parameter, a user input parameters. N is the number of toes for each experiment M. As we can see later, we can take them in input as input. But at the same way, lambda is also a user input. But in fact, here there is m, that is number of paths. There is n. N is inserted as a number of toes, but the same way is mandatory the fact that lambda can't be greater than n. It's obvious because it's very important that the parameter is between 0 and 1. So with lambda greater than n, this is not possible. So the exercise, the code is very simple. Here there is all the procedure to initialize the form that has got a picture box, 4 rich text box and 2 button. As we can see, by clicking the first button, initialize a series of several data structure as a list of intervals. There are several lists of intervals because, for example, we have to calculate at intermediate point the distribution of the success over all possibility. We take an input n as before we explained, and then we initialize a list of interval of jump that then I can show you during the execution. Then inserted the number of path, and with this procedure, with this subroutine, we ensure that the lambda is not greater than n. After that, we provide to compute our Bernoulli distribution that is each experiment is is put into these values, that is a simple array of n value. And after that, we can create some structure as point that are useful to create the random walk of our distribution. First of all, we calculate the consecutive jumps with this part of code. Then we compute the jumps into intervals. For example, we provide to divide the intervals into, as we can see, into 10 parts, 10 equals parts. And then after that we compute the statistics of our distributions of several experiments for each distributions at 2 point, half n, and at n point. After that we compute the point useful for building the graphics of random walk, and then we put our output as histogram and so on, and also histogram forms, and also with an input, a text input that is useful to understand what is the execution of our code. By sending in execution our code, I can show you which is the elaboration of our distribution. For example, if we if we click over start, here, for example, we have to input a number of random variables. For example, we put 10. I want to show you the example of with only one path, for example 1, and if I insert a parameter alpha lambda that is very small respect the number of toes, because you have to remember that the parameter for Bernoulli is lambda over n. For example, in this case 1, we can see that the distribution is very small. Is very oriented to unsuccess, a lot of unsuccess. In fact, over 10 extraction of the only one path, only one times there is a success, that is on the experiment number 6. In fact, here we can see that the distribution is between in this case between 0,1 and 0,55, and with the execution of the code, the distribution is the same, practically the same. But if we change the input, for example, for 10 toes for one experiment and lambda as a 5, we can see that the situation is quite different, because there are more than success. In this case, only one. We can try with a parameter that is huge than the before inserted, for example, in this case 7, and we can see that there is a lot of success, because the probability is greater than before. As we can see here, there is the distribution of success at half n point and at n point. These are all the success into intervals. As we can see, when there is horizontal line, there is no success, and here there is distribution of success of 1 jump in series. In fact, here we have two consecutive 1. There is one occurrence for 2 consecutive 1, and 1 for 3 consecutive jumps. If we improve our experiment, for example, with 20 toes and 5 experiment and lambda alpha, and lambda is the half of n. In fact, lambda is 10, instead n is 20, and lambda over n is the parameter that is equally perfect for success and non-success. We can see that the distribution changing. In fact, we have here a lot of random walk, as we can see before. By growing the number of experiment, distribution is more near to probability, in this case to the parameter passed as input for Bernoullian distribution. And we can see here that here there is the distribution of intervals, jump intervals, as we can see between 0 and 2. A lot of them is 9%, is a huge histogram for these intervals, and the same we can check for the consecutive number of 1. This is the distribution instead for n path at n point. We can try by growing a lot of experiment. For example, by considering half parameter, we can see that our distribution, our experiment is quite significant, as we explained it, as we expected, and the same is for a huge number of experiment, number of toes and number of experiment with, for example, is quite significant with a lambda very small. In fact, the random work is very near to the probability of failure, because there are few success. by increasing this value. For example, instead this trend is completely the opposite of the before showed. In fact, in this case, for example, there is in this case, for example, there are a lot of success on consecutive success, and distribution is growing as than before. For example, if I put 100, that is very similar, the random walk is quite significant to the success, because in every steps there is a huge probability of success. This is the C# code regarding this exercise.